Welcome back to CST432. Today we are looking into Split Personality Part 2. Some of the key concepts we will cover in this module includes movement control basics, or how we can more precisely control the movement of the robot. We will then apply this into the Tribot Robot that will be shown at the end of this presentation. And finally, we will investigate whether the use of thumb interworking can be able to reduce the code size of the executable program. What are the basics of movement control? Here I will only cover the basic concept because it can be a very complex topic to cover in robotics. So actions such as movement of robots need regulation in order to move in a predefined trajectory, or else to avoid overshooting or undershooting a target destination or position. To achieve this, we normally will use a technique called a proportional integral derivative, or PID controller, so that we are able to perform the output regulation in a controlled manner. To understand movement control, first we shall look into what is called a PID response. The PID response is basically the output that we desire from the proportional integral derivative controller. In the diagram here, we see that the red arrow points to the nicely defined response curve or line for the PID controller. We would like to move from an initial position given by the y-axis at the left and to the target value, which is called the desired output value. However, in a real system, we do not normally achieve the desired output in such a nice, clean manner. Typically, we can see different response. The first one we will look at is called an underdamped response. This means that the controller would try and reach the desired output value quickly. Unfortunately, it overshoots, and this leads to a value that exceeds the desired output value, after which it will try and compensate and bring the output value back to the target value, and eventually it will reach the target value. The next possibility is that a PID controller gives an overdamped response. What this means is that it takes a long time in trying to reach the desired output value, and this leads to the controller taking a much shallower response curve, and this may not even reach the target value in the end, as shown in the highlighted enlarged area on the right of the diagram. Ideally, we would like to see a critically damped response. What this means is that it reaches the desired output as quickly as possible without overshooting or undershooting, but at the same time, if you look closely at the range near the target or desired output value, we may see certain amount of overshooting or an undershooting, which is called a ringing response, as the controller attempts to converge to the desired output. So the convergence time needed to reach the actual output value is called the settling time. This diagram shows a discrete integer-based PID controller implementation. Now, don't worry if you do not understand most of the details here. It's just important to note that we have a command or input value equal to the desired output, y0. At the same time, after we pass through the controller, it will generate an update value u sub n, which is used to control or drive the output motor with a certain output value. So this output value will then move the motor, and the output of the motor will be a change in position. This will be normally detected by a servo, which is then used as a feedback value to be used to control or modify the behavior of the PID controller. This feedback is given in the system as y sub n, which is the output value at the nth step of the controller. So most proportional integral derivative controllers, or PID controllers, have a certain parameters that control its operation. The first is the proportional term, which handles the present conditions, and known as the proportional gain, or K sub p. The second is the integral term, which is to recover from past or historical behavior, which is known as the integral gain, or K sub I. Finally, the derivative term, which is to anticipate future behavior, is used as the derivative gain K sub d. Now all these three values control the response time of the PID controller. And in order to perform optimally, we need to use what is called the Ziegler-Nichols tuning rule to set each gain term for the PID controller so that it can try and achieve a critically damped response. To perform Ziegler-Nichols PID tuning, we need to define three parameters. First is the critical gain K sub C, second is the sample period T, and third is the oscillation period P sub C. Given these three input variables, we can then calculate K sub P, K sub I, and K sub D using the formulas given. So in the Tribot example, we have a discrete PID controller implementation. This implementation is based on the Atmel discrete PID controller algorithm, which consists of three separate files. First is the PID underscore equates.h, which defines the data structures used for the PID controller. Second is in the division.s file, which implements the unsigned long division algorithm used to calculate the values used by the PID controller. Finally, PID.s is the PID controller module, which implements the initialization, convergence, and termination routines. All these files are found in the software repository, which the URL will be given at the end of this module. We shall look at the contents of PID underscore equates.h. Here we define first a macro to perform 2's complement, because there is no native ARM instruction to perform 2's complement operation. Then we define some constants we shall need for the rest of our discussion. The maximum long value plus 1, maximum short value plus 1 are used to set the limits for checking whether we have exceeded the range of a certain value. Secondly, the scaling shift, or else known as the alpha parameter, is used to scale the values calculated by the PID controller so that we achieve better precision. Here we use a scaling value of shift of 16, which gives us a multiplication factor for alpha of 65536. Here we look at the data structure definition for the PID controller structure. The various equates here give the element offset into the data structure, including the offset for the K sub P, K sub I, K sub D, the error values, the input values, and the previous input values. This allows us to perform the PID calculation using the formula highlighted previously. So how do we use the PID controller? First, the controller must be initialized with the appropriate values for K sub P, K sub I, and K sub D. Then, once we are ready to use the PID controller, we will need to set the reference value or the target value for the controller to converge towards. And once you have set the target value, we would need to repeat this for each sample period T to get the feedback value from the output of the PID controller, using that to generate a new output value using the PID controller algorithm, and then of course program the output to the actuator or motor. And we will continue doing this every sample period T until we reach the end of the PID controller where convergence has occurred. Now we can look at the Tribot Robot, which incorporates all of what we have learned previously into a final robot software. The objective of Tribot is to be able to implement existing behaviors such as the mover robot behaviors, as well as to be able to avoid obstacles by reversing motion when an obstacle is detected. The Tribot BBR diagram is very similar to that for mover, except the addition of the ultrasound sensor, which controls the avoid obstacle behavior. Everything else remains pretty much the same. So for the avoid obstacle behavior, the main action of the behavior is to avoid an obstacle by moving the wheels backwards. Now, at the same time, the speaker also will generate a warning tone to indicate that the avoid obstacle behavior is active. The avoid obstacle behavior is triggered by the variable obstacle detected. This is set by the input from the ultrasound sensor, which collects samples and determines whether there is an obstacle in front of it or not. And once it's detected, the avoid obstacle behavior will take precedence over all the lower level behaviors. However, if it's not detected, the normal behavior of mover or grasper or the line follower would still take place. So how does the obstacle avoidance algorithm work? First, ultrasound inputs are used to detect the obstacle distance, if any. Once the obstacle has been detected at a distance less than the obstacle mean distance constant value, then the PID controller will be initialized and then will generate motor actuation outputs to move the tribot away from the obstacle. And it will reverse until the distance converges to the obstacle stop distance. This diagram is the diagram of the Tribot PID controller. You notice that this is slightly different from the PID controller diagram shown previously. The first thing is that the output from the PID controller controls a motor, and this motor output will move the actuator of the motor in a certain direction, whether forward or reverse. Now once the robot has moved, the ultrasound sensor will read the distance and detect any obstacles in front of it, and this is used as the feedback for controlling the output of the PID controller. So it is not a direct relationship between the output of the PID controller and the feedback value that is generated. So what kind of data processing steps are used for the avoid obstacle behavior? First, we have to perform input pre-processing. Ultrasound readings are noisy and it can include invalid readings from time to time. So we must not pass the raw readings directly to the PID controller as input, otherwise the PID controller will get confused. Secondly, the PID controller uses the Atmel discrete PID controller algorithm, which is detailed in the source code. The output of the PID controller will trigger motor actuation control. However, the possible output values from the controller may exceed a safe operating range for the views. So we will perform output clamping on the motor actuation output in order to limit the speeds that the tribot will use to avoid crashing tribot into objects it has detected. Let's look at the flowchart of the avoid obstacle behavior. First, we start with getting raw ultrasound inputs. And these inputs will then be pre-processed to drop any invalid readings. Next, we check the Boolean variable obstacle detected. Yes or no. If there's no obstacle detected, we then examine the input from the ultrasound sensor to determine whether the distance detected is less than a minimum distance that triggers the avoid obstacle behavior. If there is an obstacle in front of tribot, the distance will be read as being less than minimum distance. When this happens, we will need to initialize the PID controller. This is achieved using the set PID reference value to the stop distance that we have defined previously. Once we have defined the initialize the PID controller and using the defined stop distance, we will then indicate that obstacle has been detected by changing the variable to true. The PID controller algorithm is implemented as a staggered processing algorithm, which is executed once every robot scheduling duration, which is also equivalent to the sampling interval defined for the PID controller. So after the PID controller has executed, it will generate output values. You will need to check whether the PID controller has converged by comparing the target distance with the actual distance provided by the ultrasound sensors. If the target distance has not been reached yet, we will then need to send the output value to the motor actuator for programming the output controller outputs. And this output value is clamped to the speed mean and speed max for the wheels in order to make sure that we do not exceed the operating range of the wheels. Now, when the PID controller has reached convergence, meaning that the check PID end returns a yes, then we would set the obstacle detected variable to false to indicate that we have completed the PID convergence process. Now we shall look at the use of thumb interworking for code size reduction. This involves the conversion of Tribot program from the ARM code to interworked thumb code. Now we first implemented a feature complete and tested version of Tribot before we start the conversion process to study the effect of this thumb interworking conversion. And the expectation is that we will be able to reduce the object code size, since the thumb object code is for each instruction is typically half that of the ARM instructions. Secondly, we shall use UAL syntax, since the UAL syntax allows us to keep most of the syntax similar to the ARM code version. To achieve this, we must declare .syntax unified at the beginning of the the assembly source code file. And this allows us to maintain compatibility with ARM code as much as possible. So if we do not want the code to be generated as thumb code, we still can use the same instruction most of the time. Now, what are some of the issues encountered when we attempt to do conversion from ARM code to interworked thumb code? First, complex instructions must be replaced by multiple equivalent thumb instructions. Example of this is the use of multiply and accumulate, or MLA. This now becomes MULS followed by ADDS in thumb code. Secondly, all normal ARM instructions must have the S suffix added. This is because in thumb mode or thumb state, all the instructions will affect the status flags by default. So this may impact ARM's code sequences with complex logic which involve the setting of the status flags but modification of other register values before we actually make use of the original status flags that have been set. The conditional execution instructions must also be converted. Instead of using the conditional execution instructions, we must now replace it with a conditional branch instruction followed by unconditional instruction sequence, which implements the logic that was used previously. Finally, large value constants such as the address of variables need to be accessible within a reduced instruction offset range because the thumb instructions have a limited offset range for retrieving literal constants. To achieve this, we will need to use the .ltorg directive and place it somewhere within our source file where it is needed. Otherwise, the assembler will generate errors where the offset exceeds the range allowable for thumb instructions. So this table shows the output of the object size comparison between the ARM-only code and the interworked thumb code. The ARM-only code has various sections defined, which is the RxD header, init, vectors, data, text, and BSS sections. Now, most of the other sections remain identical to the thumb version. The only difference is in the .text section, which has the ARM instructions or the thumb interwork instructions in the other case. So for the ARM version, the text section has 27744 bytes, whereas the ARM interwork code section has 27272 bytes total. So there is a savings of 472 bytes if we use the ARM interwork code. However, this results only in a 1.7% reduction. So why is this so? Some comments regarding this value that we achieved. First of all, the NXOS ARM debug kernel still is predominantly ARM code. It has not changed and it forms the bulk of the output application output file. Secondly, we have only performed basic code size optimization. For example, all the thumb routines are word aligned, having word aligned start addresses, whereas they only need to be half word aligned. So there is some padding involved for each routine at the beginning of the routine. Secondly, the interwork save thumb routine return logic is used even when it is only called by a different thumb routine. So, for example, if a thumb routine calls another thumb routine, we can perform a branch and return using the program counter directly without using the branching exchange instruction. However, this was not implemented in the converted thumb code. Instead, every routine is made interworking safe so that it can be either called from ARM or from thumb routine properly. Here, let's look more carefully in the object file generated for the Tribot application, which have been written directly by us. First, we look at the various files. There have been modules that have been generated, which is division.o, helper routines.o, PID.o, and Tribot ARM or Tribot thumb.o. Division.o and PID.o are both ARM-only routines. So there is no code size reduction between the ARM code version and the interworked thumb code version. However, the helper routines have been rewritten to be interworked thumb code, and Here we see a modest reduction of 64 bytes, which is equivalent to 36.4% for that file itself. The other file, Tribot arm and Tribot thumb, sees a difference of 848 bytes. This is equivalent to a 22.4% reduction in the code size. So overall, from 4,460 bytes, we have reduced it down to 3,548 bytes, which is a 20.4% reduction. However, this does not result in the actual effective savings, because once we link it with the rest of the object code file generated for the kernel, as well as the calling from the thumb interval routines to the arm interval routines and vice versa, we have to introduce linker veneers. These veneers will reduce the code size savings to reach an eventual savings of 472 bytes, which is about 10.6%, which is quite respectable actually. So coming back to the 1.7% savings, actually the savings of about 0.5 kilobytes, half a kilobyte of memory, is in an embedded system which has a total memory of 64 kilobytes is not trivial. It may mean the difference between being able to implement all the features required versus running out of stack space and crashing your program. Secondly, if you want to achieve better code size reduction, we will need to also perform thumb interval conversion on the NXOS ARM debug kernel code. Once we converted that, we should see much better code size reduction compared to what is the case currently. Now, we should take note that not all code can be converted to thumb versions. First of all, reset and interrupt handling routines must be invoked in ARM state, and so we must have at least some instructions in ARM state even if the rest of the handlers are written to a thumb code itself. Secondly, complex algorithms that use multiple variables may not gain much from conversion to thumb code because there is a limited number of registers available for use in thumb state. So it may be more worthwhile to keep such algorithms in ARM state because we have more registers available for us to make use of. Tribot. It will try to detect any obstacle in front of it and move away. Now, I don't present a very good profile to Tribot because I am not a very solid object with a flat surface. However, I should attempt to use my hand for it to detect an obstacle. Okay, as you can see, as it's moving away, this object is a bit too heavy, so it lost the grip. As a result, it will then resume its original behavior, which is to seek for a line on the ground and move by line following. But we do not have any lines here currently. Okay, we shall try this again. It has grabbed the object, and now I shall put an obstacle in front of it. Okay, it has backed off enough for the sensor to trigger the stop distance, and so it is now waiting for the sound input again. Okay, so it tried to move forward, but it detected an obstacle and it reversed. So this is the obstacle avoidance behavior. It is in action regardless of whether an object has been detected or not. It will move back whenever it encounters an object. Now this is the PID controller taking action where it detected that it is exceeded the target range. As usual, these references will be useful if you are interested in finding out more about behavior-based robotics or the instructions used in the programs discussed previously. The PID algorithm and the unsigned long division algorithm are given here as references for the original sources. Finally, the references or URLs for the source files that are used for this presentation. See you next time.